Hey everybody, I wanted to go ahead and rehash day 2. We talked about carbohydrates again today. We got into using some of the terminology that we've previously talked about, like epimers and diastereomers and everything like that. But I wanted to expand upon what are the specific aldoses and ketoses that I want you to be familiar with for this class. Once we've established the relationship between all of those carbons and all of those sugars, I think it's also important to investigate relationships to other molecules. For instance, if we look at allose and glucose, do we have a relationship between them? Well, let's look at it. Carbons number 1 are going to be identical. Carbons number 5 and 6 are also going to be identical with the positioning of their hydroxyl groups. Carbon number 2 happens to be the same. Carbon number 4 happens to be the same. The only variation is carbon number 3. So the variation between allose and glucose is carbon number 3, making these C3 epimers. Okay, so one of the questions that I like to ask is kind of a stepwise question. It's sort of a progression. So if we want to go from allose to mannose, how can we describe that? Well, we could say that the C3 epimer of glucose is, and I shorten that to gluc, but glucose is allose. And from there, what we could also say is the C2 epimer of allose is mannose. So the relationship between glucose and mannose is bridged by the relationship between allose and mannose is bridged by glucose, because allose is related to glucose, being that they are C3 epimers, and glucose and mannose are related as they are C2 epimers. So that's one way that you could show a relationship. One thing that would not be acceptable, though, is to say that mannose is the C2, C3 epimer of allose. And the reason for that is because an epimer is variation about one carbon. Mannose and allose are related because they're diastereomers, but that's where you want to limit your relationship talk there. Now we've got kind of a similar operation here. Here we're talking about our ketoses. We have our singular ketotriose dihydroxyacetone. We have our singular ketotetrose, erythrulose, and then the only variation, or the variation, begins when we start talking about a ketopentose and ketohexose. So you can use kind of the same operation. What I like to do is I like to say de-erythrulose and draw that CH2OH CH2OH. What I like to do is I like to look at it as this is one block, this ketone group. That functional group is going to be preserved, but then carbons number 3 and 4 are also going to be preserved. So those two blocks are going to be separated from one another, and in there I'm going to introduce something new, and that is my HCOH. So I'm going to write this as CH2OH, C double bonded oxygen. Then here I'm going to introduce my new group. Then I'm going to continue on with my second block, COH, H, and CH2OH. Okay, so here I've gone from a ketotetrose to a ketopentose. I've added this rascal right here into that place right there between carbons number 2 and 3. So carbons number, I'm sorry, in the keto tetrose, it was carbons number 2 and 3. 3 become 2 and 4. This new one that I added is now carbon number 3. So when I add that in there, I have two options in which I can direct that. I could put my hydroxide group on the right-hand side like I did here, or I can make the C3 epimer, in which case the only variation is about carbon number 3. So what I've drawn is ribulose, and the C3 epimer of that is xylulose. So from those two molecules, ribulose and xylulose, I can go on to draw psychose and fructose. Psychose and fructose are C3 epimers of one another. Sorbose and tagatose, derivatives of that xylulose, those are C3 epimers of one another. It's also important to say, I'm going to write C3 eps, C3, and draw a line to connect these two, C3 eps. And then I'm going to get a different color because I think it's also important to draw other relationships. D-psychose to D-sorbose, does that have any relationship? Yes, they do. They are C4 epimers. Once you go beyond that, if you want to draw a relationship between psychose and tagatose, are those epimers of one another? No, they're not, because your variation is about 2 different carbons. The variation between, or the difference between psychose and tagatose is carbons number 3 and 4. Those are both variations of that. So you wouldn't want to say that they are epimers because of the fact that our definition of epimer is variation about 1 carbon. So that brings to a conclusion our ketoses. And now what we're going to do is we're going to go on. I like to go ahead and draw something like glucose. I like to have kind of a staple molecule that I know the structure for. And I'm going to draw D-glucose. D-glucose has the following structure. This is the linear form of it. It is a aldohexose, 3, 4, 5, and 6 H2OH. Given that is a D sugar, we've got carbon number 5 with a hydroxide group on the right-hand side. Given that is an aldose, we've got CHO up there. But now carbons number 2, 3, and 4, we've got hydroxide, hydrogen, hydroxide, hydrogen. And finally a hydroxide and a hydrogen. Okay, so this is the linear form of D-glucose. Now, what's more biologically significant or relevant and common is going to be our cyclized form. So our cyclized form of D-glucose looks a little bit like this. CH2OH we have hydroxide group going down, OH, H, and then finally, this one I'm going to draw going down. The most appropriate name for the molecule that I've drawn right here is, this is going to be alpha D glucopyranose. There's a couple of things that you need to keep in mind, or a couple of things that you can answer as to, like, where is this coming from? Well, given that it is a D sugar, it's not going to change when we cyclize it. D-gluco, so that remains. This suffix, though, this pyranose, well, the reason for that is a pyran ring is a 6-membered ring with an oxygen in it. We've got our 6-membered ring Hence, this is the pyran form or the pyranose form of glucose. Okay, so we have 1, 2, 3, 4, 5, and then our oxygen would be the sixth member of that ring. Now, I'm not going to label that just because we're going to label the carbons in just a second. Now, alpha, where on earth does that come from? That alpha designation comes from carbon 1. And specifically, the positioning of our OH group. Now, what we use in biochemistry is we talk about an alpha sugar versus a beta sugar. Alpha is the same as, or alpha basically substitutes for opposite, or terminology from organic, trans. And we're talking about this group right here and this group right here. So I like to think about these as with respect to the ring itself. So they are trans to one another. This hydroxide group and the CH2OH are trans one another, in which case this is the alpha sugar. The beta sugar, well, it looks basically the exact same. CH2OH OH, and finally OH. So this would be beta D glucopyranose. Okay, so alpha D glucopyranose, beta D glucopyranose. You have to look at where these different groups are with respect to one another. Now, the last thing that I want to talk about is the numbering of your carbons. I've already labeled carbon number 1 right here, carbon number 2, 3, 4, 5, and carbon number 6. So that's important because what do we have to form this ring? We have to have an alcohol, we have to have an aldehyde plus an alcohol. Now, when we look back at glucose, do we have an aldehyde? Yes, we do. It's right at the top here. And do we have an alcohol? Yes, we do. We have several. I'm just going to draw a little line. There's an alcohol. There's an alcohol. There's an alcohol. There's an alcohol. There's another one. The question is, well, what alcohols contribute to the formation of this ring? Well, carbon number 1, that aldehyde group reacts with the alcohol on carbon number 5. So that's something that we're going to get into a little bit more on Monday, but I wanted to go ahead and leave you all with this, and I want you to think about this term for this carbon, the alpha versus beta designation, all comes back to what is known as, this is your anomeric carbon, and the alpha versus beta designation, that freely interconverts, and that is a phenomenon known as muto-rotation. So the abundance of each of these is the alpha form of a sugar is about 33%, accounts for 33% of the molecules, and 66% are beta forms of the molecules. So I hope this helps, and I hope you have a wonderful weekend.